Okay. Two topics today. The first topic, I present one improvement of the power method for the computation of the dominant eigenvalue and eigenvector. Power method make one improvement. The second topic, preparation for the algorithm to find all eigenvalues simultaneously. Preparation for Power method only find one eigenvalue. Now I want to find all eigenvalues at the same time. We need some preparation. Take a review. What is an eigenvalue and an eigenvector? If this equation holds, where vector v belongs here, then we say that lambda is scalar, this number, an eigenvalue of matrix A, and the vector v associate eigenvector. Eigenvector associate with this eigenvalue. So we want to find out all such scalars and such vectors. With real number 2. Theoretically, this is a theoretical. Theoretically. To find eigenvalues, all eigenvalues, solve this polynomial equation. Determinant A minus lambda I is identity matrix is 0. Solve. Determinant, after you expand determinant, you will see a polynomial of degree n in lambda. This is a polynomial. Solve this polynomial for the zeros, then those are eigenvalues. But this is a theoretically works. Computationally doesn't work. Why? Because expanding the left-hand side, impossible, almost impossible, when size is large. I have one example at the beginning of the semester. When n is 20 by 20 determinant, expand a 20 by 20 determinant by a supercomputer. It took many years, So if n is large, usually n very large. How large? Billions, billion by billion. The matrix. Common, nowadays. Review number 3. Power method, Power method, number 3. Power method. Power method has some assumptions. Assumptions. Assume. Number 1. Matrix A is a real matrix. We don't consider complex matrix. But of course, in literature, there are many research about complex matrices, but here we assume A real matrices. real is a matrix. Okay. And number two, A has n linearly independent eigenvectors. Eigenvectors. Okay. I say psi 1, psi 2, and psi n. And the corresponding eigenvalues is corresponding eigenvalues. Lambda 1, lambda 2. Yeah. Okay. Lambda 1, lambda 2, and lambda n. Okay, now further, we assume one eigenvalue dominate larger than all other eigenvalues in absolute value. Yeah, in absolute value. Okay, and further we assume, okay, lambda 1 is eigenvalue in absolute value greater than all other eigenvalues. Okay, where I is 2, 3, and n. And also assume, okay, eigenvalues and eigenvectors all are eigenvalues, of course, real numbers. So R. Vector is the notation is Rn. Okay, yeah. Real and in Rn. Rn. A matrix is n by n. Yeah. N by n. That is the set of all matrices. This is the set of all numbers, real numbers. The set of all real vectors. Okay, now what is power method? Power method. Find. Compute lambda 1. Okay, this is a power method. Only one eigenvalue. The dominant eigenvalue. Power method. Compute. Okay. How? Power method. Yeah. How power method works? Power method. Step 1. Take a vector. Okay. Take a vector. Yeah. Arbitrary pick. Okay. Take a vector. And because psi 1, psi 2, psi n, they form a basis for Rn. Yeah. N linear independent vectors is a basis of Rn. Basis. So I can express V as a linear combination of these vectors. Yeah. I can write, okay, write C1, psi 1, C2, psi 2, Cn, psi n. Because I don't know the eigenvectors. I want to compute them. I don't know the eigenvectors. So I don't know what is C1, C2, Cn. But I'm sure they exist. Even though I don't know them, they exist. Okay, now apply AK, okay, A to K, A times A times A times A times A, K times. Okay, to the left side and to the right side. To the right side. Okay. I assume psi 1, psi 2, psi n, they are eigenvectors. So we have A times psi 1 is lambda 1 times psi 1, right? That is the definition of eigenvector and eigenvalue. So, okay, now, so apply A to this equation. Yeah. Okay. This is a definition of eigenvalue and eigenvector. Now multiply the equation by A, then I get this equation. So the A times psi 1 is this. So lambda 1 squared psi 1. In general, this is a C1 lambda 1 K psi 1. And this is a lambda 2 K psi 2. And so on. Lambda n K psi n. Okay, now take the dominant eigenvalue out, factor out. Okay, so you get lambda 1 K times C1 psi 1, then plus C2. Take lambda 1 out, so lambda 2 over lambda 1 K psi 2 Cn lambda n lambda 1 K psi n. Don't forget this assumption. When K lambda 2 over lambda 1 is a number less than 1. So when K is large, except the first term, the other term, all other terms are very close to 0. So roughly is lambda 1 K CK psi 1. All the other terms are 0. So this is for K very large. This symbol means K much larger than 0. Very large. Psi 1 dominant eigenvector. Eigenvector multiplied by a scalar, still an eigenvector. This is a scalar, a number. Okay, a number times an eigenvector, still eigenvector. So AK times B, when K is very large, this is close to the dominant eigenvector. This is a power method. Okay, so power method is here. Power method is so the algorithm for power method is here. Right? Power method. Step 1, pick a vector in Rn and set V0 BV. Now step 2, compare VK. What is VK? VK is AK times V0, right? Here, this one. So this is what? This is A times VK minus 1. So when K is large, this is eigenvector, the dominant eigenvector. How to compare eigenvalue? How to compare lambda 1 eigenvalue? Eigenvalue. VK, VK. So let's pick one Vk is a vector. Pick one entry. Say the entry at position I. Yeah. Yeah. Let me below this. Yeah. I. Okay. Yeah. This location means a vector. Yeah. Position I. Position. A vector has n entries. Now let me pick the I entry. Yeah. Take a look at this ratio. Okay. K minus 1. This is a lambda 1. How? Okay. How? Roughly. Okay. Not exactly. Okay. This is a lambda 1 K C1. Then psi 1. I. Then this is a lambda 1 K minus 1 C1 psi 1. Then I. Yeah, from here. Now, a number times a vector, the ith entry. So actually, I can move the number up. 1k times c1, then times psi 1, this vector, the ith entry. Lambda 1 k minus 1 c1 times psi 1 I. Okay, now all are scalars. Yeah. Yeah. Scalar. This is a vector. Then take the I entry scalar. So job. Okay. So yeah, this is and this is lambda 1. So lambda 1 roughly is this. Okay. Now compare. Compare VK yeah, I entry, yeah, VK is vector available over VK minus 1. Yeah. That this is roughly lambda 1, the dominant information. This algorithm has a drawback. Okay. From here, I have erased. This is roughly equals to what? Equals to lambda 1k times c1 times psi 1. Yeah. I have erased. Hey, now there is a problem. When lambda 1 greater than 0 in absolute value, right? If lambda 1 greater than 0, then we can see that this the length, yeah, too long is length, approach infinity. Too long. What is too long? Yeah, a vector too long. Yeah, a vector too long is square root first entry squared, second entry squared, Vn squared. Yeah. This number is called too long of vector V, a vector. Yeah. Actually, it is the length of the vector. And the other case, if lambda 1 less than 1, then Vk will drop to 0. But this ratio, in some cases, this ratio may converge to number 1 slowly. when K is large, this is still far from lambda 1. This is possible, but Vk already very large. So large that your computer cannot contain this vector. So in the case, we call the computation overflow. But the other case, underflow. Yeah, this go to 0 very fast, but still this still very far from lambda 1, the case underflow. So now, today I want to make improvement. Okay, I don't want this guy go to infinity. I don't want this guy go down to 0. What we can do here, after we compute Vk, normalize Vk, make Vk this vector into a unit vector. Unit vector, the length is 1. Okay, this is what I want to make improvement. Yeah. This is today. Okay. Today. Today, okay. Now let me normalize the vectors. Okay, first. Oh, why all the markers are all unreal, but okay. Psi 1. Psi 1 is dominant eigenvectors. Let me normalize it. Okay, yeah, here. Half divided by its length. Eigenvector divided by a number or multiplied by a number, still eigenvector. Let me denote it by eta. Okay, eta 1. I want to find eta 1. How about Vk? Yeah, Vk. Yeah, Vk here. Yeah. I compute Vk. Okay. I also normalize Vk. So make the vector, the length is 1. Okay, don't go to infinity. Don't go down to 0. Okay. Now let me denote it by U. Uk. Yeah, U. Unit vector. U. Okay. Now then it can be proved. Then depends on the case. Okay. When k approaches infinity, okay, uk is unit vector will approach eta 1 eigenvector. This is an eigenvector, dominant eigenvector. Then we want to find. How about uk? Uk, yeah, obtain in this algorithm, computable uk. Then this unit vector will approach eta 1, this eigenvector. Of course, in the front there is a scalar. Okay, psi C1. What is C1? Recall, we can always write V. What is V? V is 0. Okay, yeah. Arbitrary pick. We can always write V as a linear combination of eigenvectors. Yeah. So C1 is the C1. What is sine? Yeah. Sine of a number, say number 3. Then sine of 3 is positive 1. This is a MATLAB function. Sine of 0 is 0. Sine of negative 100, it is negative 1. So sine of C1, either 1, 0, or negative 1. Yeah, this vector approach is. If lambda 1 greater than 0, what is lambda 1? I want to find it. Okay. I want to compute it. Lambda 1, the dominant. The dominant eigenvalue. B. Okay. Negative 1 k times u k will approach sine C1 times eta 1 if lambda 1 less than 0. Right. But these two statements says that yeah. What is this statement says? This statement says UK roughly is sine C1 eta 1 when K large, super large. So when K is super large, UK. Here, after I compute VK, normalize VK to get UK. When K is large, UK is a number times eta 1. Eta 1 eigenvector, dominant eigenvector, unit eigenvector, length is 1. Here, 1 to k, UK is sine C1 eta 1, right? Right. When K very large, but again, I move negative 1k to the right side, so UK is negative 1k sine n C1 eta 1. This is when roughly, okay, not equal, roughly. Negative to k sine of C1, a number. A number times eigenvector is still eigenvector. So in any case, I compare VK, then normalize this vector to get UK. UK roughly is eigenvector. Yeah. Dominant eigenvector. Okay, now this is about eigenvector. Now, how to find eigenvalue? Yeah. Right. How to find eigenvalue? Is one. How to find it? Okay, now here. Right. Also, two cases. Okay. Yeah. This case first. This case first. K approaches infinity, UK approaches this vector. Now I multiply A to these equations. So here. Limit K approaches infinity, A times UK is equal to sine C1 times A eta 1. Right, you agree? Yeah. I multiply A to left side. Multiply A to the right side. Then I get this equation. Eta 1 eigenvector associated with eigenvalue lambda 1. So sine C1 times lambda 1 times eta. Yeah. Okay, now consider this ratio. Consider. Okay. Consider, okay. A times UK. Yeah. Take, this is a vector. Take one entry, say entry, the ith entry. Yeah. Then over UK, this vector, the ith entry, okay. Ith entry. So roughly, okay, is equal to, yeah, what is A times UK? Yeah, A times UK approaching this, okay. So this is a sine C1 lambda 1 times eta 1, yeah, I entry, then over UK, yeah, this case, okay, UK, when K is large, about this, so this is a sine C1 eta 1, okay, a number times a vector, the ith entry, yeah, yes, this is equal to, I can move number up, sine C1 times lambda 1 times, okay, vector eta 1, the ith entry, over sine C1 times eta 1 I. Okay, now cancel, yeah, is lambda 1. This ratio roughly is dominant eigenvalue. Similarly, this ratio also dominant eigenvalue for B, okay, for B, for this case. The argument the same. Okay, now let me rewrite this algorithm. Improve power method. Okay, yeah, this is a improve power method. Okay, yeah, I want to keep, I don't want, VK go up to infinity or go down to infinity. Okay, now arbitrarily take a vector V and set V0, normalize the vector. Okay, yeah. Normalize over the length. Here V1, V0, unit vector. Okay, unit vector. Okay, now compare. Now compare what? Compare this. Okay, VK is A times VK minus 1. Yeah, compare this. Compare. When K is 1, then V1 is K times V0, V0. After we compute this, here, compute this. Don't normalize at step 2, because we need to compute this. Okay, we need compute eigenvalue. Yeah, eigenvalue is here. Yeah. A times UK. Let me change. This is U. Okay, unit vector. Okay, U. Okay. This is U. Yeah, U means normalized. Okay. Now this is U. But this U not normalized yet. Okay, because I know A times UK not normalized. Then take the I entry over UK. So okay, now after I compare this, then okay, compare eigenvalue. A U K I entry is over U K minus 1. Yeah, the I entry. Here, complete this. Yeah, this is a roughly lambda 1 when K is large. But this is a what? A times U K minus 1. Yeah, from the previous step is a K U K I entry over U K minus 1. Right, you okay? Yeah. This is about dominant eigenvalue. Yeah, here. But A times U K minus 1 is UK. So UK. All right, now let me erase. All right, now step 4. Okay, step 4. Normalize this UK. Yeah. We haven't normalized it yet. They're not normalized. Okay. UK K is UK divided by its length. Okay, normalized. This is when K is large, this UK roughly is eta 1. Roughly eta 1. Eta 1. Okay, now this is a improved version of power method. Now let me apply this algorithm to the same matrix in the last class. Okay. The same matrix. Yeah, here. Example 1. Consider this matrix. We solved this matrix by power method in the last class, but we saw that the eigenvectors go up to infinity. Okay. Exact eigenvalues. Number 3, dominant. Number 2, -2. Number 3, 1. The dominant eigenvector is 1, -1, 3. Yeah. Of course, this vector, the length is not equal to 1. Okay. Yeah. UK approaches dominant eigenvectors with length 1. Yeah, you need to normalize this. Yeah. Eigenvector associated with this is a 0, 1, -1. Yeah. This vector, again, the length, log 1. And this is a -1, 1. Now, make a table. Okay, make a table. Yeah, make a table. Table. K, yeah, iteration number. K. Okay. This is a U K. Yeah. UK. Yes, UK. And the last column is U K. Entry 1 over U UK minus 1, actually. UK minus 1. UK minus 1. UK minus 2, right? UK minus UK. Oh, A times. Okay. A times. Yeah, here. A times UK minus 1 over UK minus 1. Okay. First entry. Yeah. 1. Okay. 1. Okay. Now, when K is 0, okay, when K is 0, yeah, the vector V, then normalize it, okay. 1, 0, 0, yeah. 3 entries. First entry 1, second entry 0, 0. K is 0, so K is 0, U to -1. No value. Okay. K is 1, then this is a -0.95, and this is a -1. The last column, estimate the dominant eigenvalue. Yeah. Yeah. The length of this vector, if you compute it, the length is equal to 1. Yeah, this vector. Don't keep it, don't go to infinity. K is 2. Then 0.2335, 0.3669, then 0.9005. Yeah. Then 7. Okay. So this vector, the length is 1. Keep it. Don't let it go down to 0 or go up to infinity. That vector. Run this everything. Okay. K is 11. Then 0.3028, 0.2993, 0.29048. Now, the last column will approach eigenvalue 3, 3.0001. Yeah. Dominant eigenvalue. One more step. Go. 0.3007, 0.3037, 0.9043. Now this is a 30000. Converge. Yeah, this is a eigenvalue, and this associate eigenvector with length 1. This is an improved power method. Power method look for dominant eigenvalue. Actually, if you want to find the smallest eigenvalue, what we can do. Okay. Yeah, actually, there are some other versions. Yeah, some other applications of power method. Yeah. All right. So let me consider two cases. Okay. Case one. Okay. Find the smallest eigenvalue. Okay. Lambda 1 greater than lambda 2. In absolute value. Okay. Greater than lambda n minus 1. Okay. Lambda n smallest in absolute value. If I want to find lambda n, then what we can do? Okay. Power method, look for lambda 1, the largest eigenvalue. If I want the smallest eigenvalue, easy. Apply power method for A inverse. Okay. Why? Because A inverse eigenvalues. Okay. Eigenvalues of A inverse is 1 over lambda 1, 1 over lambda 2, 1 over lambda n. Yeah, eigenvalues. Okay, now 1 over lambda 1, lambda n in absolute value dominant. Okay, right? Because smallest when you take inverse, largest. So you can apply power method to this matrix. Look for the largest eigenvalue of this. After you get the largest eigenvalue, then 1 over the eigenvalue to get the smallest eigenvalue. Second case. How about we want to find I eigenvalue between the largest and the smallest? How? Right? Yeah, you can do that in this way. Take a number, mu. Right? Of course, real number. Okay. Then consider this matrix. Mu. Consider this matrix. The eigenvalues of this matrix is 1 over lambda 1 minus mu, 1 over lambda 2 minus mu, 1 over lambda n minus mu. Yeah, this matrix, all the eigenvalues is this. Now, apply power method. Power method to this matrix. Then power method find the largest eigenvalue for this matrix. I don't know. The largest maybe depends on which lambda is closest to mu. When lambda closest to mu, 1 over the number is the largest. Right? Apply power to this matrix to find lambda I that is the closest to mu. Okay. That makes sense? Yeah, if you want to find, pick a mu. I want to find, okay, matrix A. The eigenvalue that is closest to mu, then apply power method to this matrix. Then the dominant eigenvalue of this matrix is the eigenvalue of A, lambda I, that is closest to mu. This is for today. Monday, I want to present a method. The method not just compute one eigenvalue. Power method compute only one eigenvalue. I want to present a method that compute all the eigenvalues at the same time. Okay, simultaneously. Yeah. Monday.